Good morning. I hope you're enjoying VICCE. I will present our paper titled Case Study of Nearshore Currents Hazard Analysis for Recreational Beach Development. This paper is sorted from our project study for Coastline along Palawan. I am Cruz. This paper is co-authored with engineers Clint Reyes and Eric Santos. This is an outline of my presentation. For the background, two coastlines that have characteristics of a good beach resort are being considered along the western coastline of Palawan, located here, and this is the capital, Manila, which is just to the north. There are two resort locations that are being considered. Location one, which is at the southern coast, and location two, which is to the north. There have been reports of rip currents along the two coasts. So this study also aims to confirm that. There are some features of these two locations. Location one has a curved coastline of about 4.9 kilometers. It is bounded on the west by a headland and on the east by an elongated embankment that acts as a groin. Location one has an intertidal zone of about 20 meters and slopes are roughly 8%. There is an escarpment of height 0.4 meter. Location 2 is along a relatively long coastline, a straight coastline of about 5.6 kilometers. It's bounded to the south by a headland and to the north by a rocky islet. The islet is about 100 meters offshore and sustains a mud salient that's visible during the summer. Nothing is photo. This coastline has an intertidal zone of 29 meters and slopes about 5%. The objectives of the study are as follows. Describe the features that along the two study coasts that impact the local hydrodynamics and wave processes. Determine the offshore wave conditions to be used in analysis of wave climate and currents. To carry out hydrodynamic simulations to determine wave-induced currents during the two seasons of amihan and habagat. And finally, to provide recommendation on current thresholds for safe active swimming in these coastlines. The wind data. Here's the offshore wind loss diagram that's available in Pag-asa, the country's meteorological agency. At the nearest similarly exposed wind station in Pag-asa Island here, you can see that the winds blow most frequently from northeast and southwest. The highest speeds correspond to sustained speeds of 13 to 16 meters per second, which are just below the minimum speeds of tropical depressions. Now the depth data. Here's the consolidated bathymetry map. Note the depth range here. That's from 0 to around 200 meters. Here's the offshore sea boundary, and this is the north open boundary, the south open boundary, and here's the relatively small region of the study coast. The depths here are less than 40 meters. Zooming in into the nearshore bathymetry, here are the local depths in location one. This is the natural groin, the south headland, and the north headland. The distance to depths of 6 meters is about 800 meters. For location 2, here's the rocky islet and the south headland, and distance to 6 meter depth is a mere 150 meters offshore. To determine the wave climate, we employed a hydrodynamic model in the regional domain to provide boundary conditions for water levels and currents. Here are the governing equations, governing nonlinear shallow water equations of mass continuity and momentum. The dependent variables are zeta, the sea surface displacement, and P and Q are the Cartesian components in the horizontal plane. The momentum equations account for the convective accelerations, the bottom resistance, the viscosity related energy dissipation, the Coriolis acceleration, the wind shear, and the atmospheric pressure gradient. When expressed in multiple scales, these equations are second order in zeta. The numerical model for waves is based on the wave action equation, where N is the wave action density containing the wave energy term. The wave field variables are solved from the wave conservation equations, and the energy density from the wave action equation. These equations yield the wave height and the wave direction fields. The wave action equation is solved within the NEARSHORE domain to generate the wave field induced by an imposed surface wind field, wave energy input through the boundaries, and the computed hydrodynamic field. Wave boundary conditions are obtained from an offshore wave hindcast based on wave fetch and wind speed at 10-meter elevation. The wave conditions along the NEARSHORE boundaries are based on wave hindcast for the significant wave height and period. The coupled model was calibrated using recorded data of water levels at two government tide stations, namely Balintang here and El Nido. These are located about 200 kilometers to the south for Balintang and about 75 kilometers to the north for El Nido. And have shallow depths of 1.4 meter and 2.4 meter. These plots, the lower plots show the comparisons of the time series of water levels at the two stations for a duration of 5 weeks beginning February 2016. The upper plots summarize the QQ plots of water levels at these two stations. The coefficients of determination are very good, at more than 93%. And the bias comparisons are also excellent for the two stations. This table shows the hindcast offshore wave conditions. The prevailing directions of offshore waves are northeast, southwest, and north-northeast. However, the highest offshore waves approach from the west-southwest, the southwest, the west, and from the north. These offshore conditions are inputted into the quasi-stationary numerical simulations of water levels, waves, and currents. The water level, wave, and wind fields are inputted into the coupled hydrodynamic and wave models from which the NEARSHORE currents are synthesized. This slide shows the simulated rip currents at 3 stages. The generation stage, the upper plots here, and the peak stage, the middle plots, and the recession stage, these are plots. For equation 1, the left panels here, the rip currents reach about 0.35 MPS. and they are seen to be generated in front of coastline sea by winds and offshore waves from the north. For location 2, the right plots, no? Milder and smaller, no, rip currents of intensity 0.3 meters per second are formed at the south side, no, of the rocky islet, no, by winds and waves from the west. To the along the coastline of location 2, strong longshore currents, no, of intensity of 0.8 MPS, no, are seen to be generated by offshore winds and waves, no, from the west-southwest and from the southwest. The various offshore wind and wave conditions were likewise simulated. In summary, here are the directions of winds and waves that generate, no, nearshore currents at locations 1 and 2 in this column, and location 2 for this column. The peak rip current intensities are 0.5 MPS, no, due to the north approach in location 1, and due to the northwest approach in location 2. To determine if the simulated rip currents are safe for active swimming when these coastlines are open, a simple stability analysis was carried out. No? The human body is idealized as a vertical cylinder, no, with assumed drag and inertial coefficients, no, body dimensions as shown here. It is found that the overturning instability is more critical, no, than the sliding. To cause overturning of an average adult, no, a rip current intensity of at least 0.16 MPS is needed in the depth of 1.6 meters. We examined all the simulation results to identify the zones in the 2 locations where the rips are formed. Where there are none, or when rips are weaker than about 0.1 MPS, no, that's lower than 0.16, no, the zone is considered safe. No? Longshore currents that are lower than the same threshold of 0.1 MPS are considered safe. This slides shows the safe swimming zones, no, during the prevailing conditions. For the summer months of March and April, no, the safe swimming zone are as shown. They are larger in area, no, than in location 1 than in location 2. In conclusion, it is found that the generation of these nearshore currents, no, is highly dependent on 3 main parameters: the nearshore bathymetry, the incident wave approach, direction, and the coastline shape. Also, results show that generation of rip currents on long continuous coastlines is prevalent, no, for both sheltered and open beach coasts. Assessment of human safety with respect to nearshore currents was undertaken. It was determined that for an average depth of 1.6 meter, a current threshold of 0.16 meter per second may be used. And finally, this paper recommends a methodology of identifying the safe swimming zones along a project course by carrying out a simulative analysis of the nearshore currents and comparing the same with human safety threshold. Thank you for listening.